Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. I want to welcome you. I'm Yvonne Stapp for Science for the Public. And we have tonight Einstein's Relativity, and Dr. Tereasa Brainerd is the Associate Chair of the Boston University Astronomy Department and the Director there of the Institute for Astrophysical Research. She received her PhD in astronomy from Ohio State University in 1992, where her research focused on the use of computer simulations to constrain growth of dark matter structure in the universe, a mouthful. Professor Brainerd did postdoctoral work at Caltech from 1992 to 1994 and at Los Alamos Lab from 1994 to 1995, and then joined the astronomy department at Boston University. She's best known for her work in weak gravitational lensing and faint galaxy clustering and locations of satellite galaxies relative to their hosts. And her most recent work involves measuring the degree to which galaxies are intrinsically aligned with each other over large scales of the universe, in the universe, I should say. Dr. Brainerd is going to talk to us tonight about Einstein's relativity theories, the general theory of relativity, the special theory of relativity, and how these theories have reshaped our understanding of nature and the cosmos. She brings to her discussion a very wide perspective and extensive experience in the application of these theories. I'd like to mention she's also very committed to improving communication between the scientific community and the general public, and that's why she's with us tonight. So we are indeed very honored to have this outstanding scientist with us. Please welcome Dr. Tereasa Brainerd.
Thank you for the lovely introduction. I hope I can live up to it. Good evening, everyone. Hopefully, most of you heard on your way in as we were settling down the music that was playing. I chose the song very specifically. It's a song off a very famous album called Night at the Opera by Queen, which has a number of famous songs on it, like Bohemian Rhapsody, You're My Best Friend. People know these songs. The song I played for you is not one that's very well known. It never got any airtime, and it confuses the heck out of most people. Most people who listen to it think, what's going on in this song? It's a song about relativity. It was written by Brian May, who was the guitarist for Queen. At the time, he had a master's degree in astronomy, and he has since gone back and got his PhD in astronomy. And he knew an awful lot about exactly what we're going to talk about tonight. The song is titled 39, and what happens in 39 is a group of travelers leave the Earth and they come back. They leave in the year of 39, they come back in the year of 39. And you might think, well, that's, they did it within 1 year. But in fact, they didn't. What happens in the song is the travelers travel for 1 year, they age for 1 year, but when they get back, 100 years has passed on the Earth. And that's what we're going to talk about tonight. We're going to start with time travel. And we're going to ask, is it possible to do time travel the way the volunteers in 39 did? And it's going to turn out that Einstein will say yes, but there's some really important caveats. The first caveat is you can only go forward in time. You can only go into your future. It's also not possible to travel in time instantaneously. You have to devote some time to actually going into your future. And the last is going to be, you have to be going very fast to pull this off. We're going to talk about relativity as Einstein thought about it. And we're going to talk about things that we experience in our daily lives and discover that things that we hold near and dear to us are not as absolute as we might think. There are a number of non-intuitive results that we're going to see. The first one is what we mean by motion is actually relative. Time is also something that is not absolute, it's relative. Distance is not absolute, it's relative. We're going to see all of these things tonight. How are we going to do this? How are we going to understand this? The understanding starts with Newton's first law of motion. That's the law of inertia. And we need two people, two observers, one of whom is going to move in a straight line at a constant speed with respect to the other one. And we're going to ask, does everybody see Newton's first law of motion? And if they do, what do they say are measurements of time and measurements of distance? There we go. Okay, we're going to start with the special theory of relativity. Special theory of relativity was what Einstein was doing in 1905. And a perfectly reasonable question is, what's special about special relativity? And the answer is simple. What's special about special relativity is that there are no accelerations going on. There's just uniform motion at a constant speed. And very specifically, technically, there's no gravity. Gravity causes an acceleration. To talk about relativity, we need to talk about reference frame, your point of reference or somebody else's point of reference. And in special relativity, the reference frames that we're going to talk about are something called inertial frames of reference, where the observers are not accelerating and Newton's first law of motion is observed to hold. What's Newton's first law of motion? Newton's first law of motion says an object will remain in a state of uniform motion in a straight line or in a state of rest until acted upon by a force. But what's a state of rest? What's a state of motion? You might think those are silly questions, but they're not. It's all about relative motion, somebody moving relative to somebody else. We need two people, two observers. One is going to move with respect to the other in a straight line at a constant speed. So we'll take two people. One person is going to be a passenger on a train that's traveling on a straight track at a constant speed with respect to the ground. The other person we need is a bystander who's going to stand next to the train tracks, watch the train and the other observer go by. Simple enough. I teach at Boston University, right on Comm Ave. We use the T all the time. Okay. Let's build a train. Long-distance train has a dining car on it. There's the dining car. The train is going to move off to the right at some constant speed, v. We take our observer, who is a passenger on the train, we sit her down at a table in the dining car, and we put a bottle of wine on the table. And we ask her, does Newton's first law hold for your bottle of wine? And she will say, yes, absolutely, until I pick the wine up and pour myself a glass. That bottle of wine stays in a state of rest on the table. Okay, so she says Newton's first law applies to the bottle of wine because it's in a state of rest. But you ask what the bystander says. The bystander says, no, wait a minute. It's going past me at a constant speed. The bottle of wine is in a state of uniform motion at a constant speed. So the bystander also sees Newton's first law, but he sees it as uniform motion. And this is one of the keys. What we talk about as a state of motion is not an absolute statement. It depends upon your frame of reference. So in this case, both of our observers see Newton's first law. They're both in an inertial frame of reference. But the very idea of what is a state of motion is a relative concept. Relative to the table, the passenger says the wine isn't moving. Relative to the ground, The bystander says, yeah, that bottle of wine is moving. Important little point. Important little point is something called reciprocity. The passenger on the train has an equal right to say that she is at rest, and the world is simply whizzing past her in the other direction. Neither person that we're actually talking about has a valid claim to even be at rest, because the idea of rest and motion are relative. I am in a state of motion, or I am in a state of rest, are actually not valid statements. What's special relativity all about? There are two postulates that go into special relativity. The first is that the laws of nature are the same in all inertial frames of reference. Everybody sees the same physics, whether you're on the railway platform or if you're on the train. The other postulate is that the speed of light in vacuum is the same in all inertial reference frames. And what Einstein is saying here is that light is very different from baseballs. Okay? If you give somebody a baseball and you put them on the tee and you ask them to throw the baseball down the train, you can measure the speed of the baseball with respect to the seats on the tee, and you can measure the speed of the baseball with respect to the train tracks under the tee, and you'll get different numbers. And what Einstein says is, you take a laser pointer and you measure the speed, you get the same number whether the tee is moving or not, on the tee and moving down Comm Ave. We're going to see that these two postulates result in two very unsettling consequences that come out of special relativity. Two things that in your everyday life I bet you hold near and dear are that measurements of time are relative. Two people, one a bystander watching a train go by, the other a passenger on the train, will measure different lengths of time between two events. The other thing you probably hold near and dear is measurements of distance. Everybody agrees on how long a meter stick is, right? Not actually. Not if you live in Einstein's universe, living close to the speed of light. We're going to do a little Gedanken experiment, a little thought experiment. We're going to need some clocks, we're going to need some rulers, and we need our two people, our passenger on the train and our bystander. We're going to give our two observers identical clocks and identical rulers. So if they were both sitting here before we send them off to do the experiment, they would agree, yes, our clocks are the same. Yes, our rulers are the same. We're going to put them in a state of relative motion, and we're going to ask them to measure time intervals and distance intervals. We're going to do a little teeny tiny bit of algebra. Not much, a little bit. We'll call T sub P the time that our passenger measures, T sub B the time measured by our bystander. We'll measure distances too, where D sub P is the distance measured by our passenger, and D sub B is the distance measured by our bystander. And the whole key to this is our observers are in a state of relative motion. One is moving in a straight line at a constant speed with respect to the other. And we're going to ask, will they agree on measurements of time and distance? Simple first experiment. We're going to measure the passage of time. And the way we're going to do this is we're going to put a light in the floor of the train car. And we're going to measure how long it takes light to go up to a mirror in the ceiling of the train car, bounce off, and come back down. Okay? So we ask our passenger on the train to do this. Measure how long it takes light to go up to the mirror, come back down again. Well, that's easy. If the height of the train car is little h, you know that time is the amount of distance you've traveled divided by your speed. The total distance is once up, once down, so that's 2h. How fast is light moving? It's moving at c. Einstein tells us for all inertial reference frames, the speed of light is c, 300,000 kilometers per second. So the time our passenger measures is twice the height of the train car divided by the speed of light. Okay. Now, This never works with the laser pointer because I can't move fast enough and the light moves really, really fast. Okay, can you see that spot on the ceiling? Okay, so that's our spot. If I were in the train car, this is what I would be seeing, just bouncing up and down. But what I now got to do is this, okay? So from your perspective as a bystander, that source of light is moving past you. And we have to do a little tiny willing suspension of disbelief. You have to imagine the most impossibly fast freeze-frame camera. And I want you to imagine not a beam of light, but a single particle of light emitted by the light bulb, and ask, what's the path of that particle of light as it goes up to the ceiling of the train car and comes back down? Most importantly, what is the path of the light that you see watching the light move past you? So here it is, laid out step by step by step. Here's the start over on the left. Here's the end over on the right. This is what you as a bystander would see if you could film it with the most amazingly high-speed camera. Here's a single particle of light. It leaves our light bulb, and it's headed straight up to where the mirror is. But the mirror is going to move, and the mirror is going to move, and the mirror is going to move, and so is the light. So there's our particle of light. It's left the light bulb. It's now up here. It's now up here. It gets to here. It hits the mirror, and it reflects, and it comes back down, straight down to the light bulb. But the light bulb and the mirror have moved. So the path of the light is not straight up and down. It's a triangle. See that? Up and down. So how long does the bystander say it took that light to go up to the mirror and come back down again? Well, you need to know what the distance is. There's the height. The length of the path of the light is just twice this distance, call it d. Two sides of two right-angled triangles, if you remember your geometry. The time that the bystander measures is twice that distance d divided by the speed of light. But obviously that distance, the hypotenuse of the triangle, is longer than the height of the triangle. So in other words, necessarily the amount of time that our bystander measures for the light to go up in the triangular path and come back down is longer than what our passenger measures. The bottom line here is, if you think of this as a clock, a light clock, where going up is tick, coming back down is tock, the moving clock is running slow relative to a stationary clock. That's what's called time dilation. It's one of the first funny things that comes out of special relativity. Our bystander, watching this whole thing go by, says that time is running slowly on the train compared to his own clock. So the first thing we see is that measurements of the passage of time are not absolute. They're relative. They depend upon a state of relative motion. What about distance? Whoops, sorry. I meant to mention this. If you remember your Pythagorean theorem, a little bit of patience, a little bit of algebra, and you can figure out exactly what the difference is in terms of the time. The time measured by the bystander for the light to go up and down in the triangular path is the time measured by the passenger divided by the square root of 1 minus the square of the speed of the train divided by the square of the speed of light. That's something that I'm going to write as the Greek letter capital gamma. We're going to call it the boost factor. If you've ever actually seen this taught in an undergraduate physics class, this is also called the Lorentz factor. But the point is, there's a simple number that relates through the speed of the train, the time measured by the bystander, and the time measured by the passenger. And the faster the train goes, the bigger that boost factor becomes. Which is why you don't notice this if you're going at speeds that are very small compared to the speed of light, because for all intents and purposes, if you let v be 0, the boost factor is 1, you get the same result. All right, distance. Let's measure distance, again using our train. We've got two trees, one there, and those trees are genuinely motionless with respect to the train tracks, okay? They're fixed, they're in the ground, they're growing. And we're going to measure the distance between the two trees by using speed of the train and the time it takes to go between the two trees. So distance is just speed times time, right? So the distance that our bystander measures is the train comes along here, moving at some speed v. When it gets there, our bystander clicks his stopwatch and times how long it takes the train to get to there. Okay, so that's the distance between the trees. Do the same thing for the passenger. Give the passenger a stopwatch and say, when you get right here, start your stopwatch. When you get right there, stop your stopwatch. And the distance that you measure is the speed of the train times the time that you measure on the train. Simple enough. But we already saw the time is running at a different rate. It's running slower on the train than it is for our bystander. So because our bystander measures a longer period of time, our bystander actually says the distance between those two trees is longer than the passenger says, and it's exactly that same boost factor. The passenger measures a shorter distance than does the bystander in his direction of motion, and that's something called length contraction. Again, it's not something that you notice in your everyday life. That's my campus. That's Marsh Plaza. It's Marsh Chapel right there. That's the Great Seal of Boston University. Imagine you're on a B Green Line train and you're rolling down Comm Ave. If you're rolling down Comm Ave at the speed that the T normally goes down Comm Ave, which is like a couple miles an hour, and you look at Marsh Chapel, it looks normal. The trees look normal, the people look normal. In the far distant future, when there are no lights on Comm Ave, and the T has been accelerated up to very high speeds, what happens? Let's let this T go at half the speed of light. Did you notice that it shrunk? Forget that for a second. If you look at the perspective, you wouldn't say there's anything funny about that picture unless you really happen to know the dimensions of Marsh Chapel. But in fact, it has shrunk. Go to 3/4 the speed of light. Things are getting kind of skinny. They're not getting taller. They're only getting skinnier. Go a little faster, 85% of the speed of light, and that perspective is starting to look very strange. Go even faster, 95% of the speed of light, and everything has shrunk in the direction of motion. So just because it's fun, we'll go all the way back to the beginning, and as you accelerate the T up to 95% of the speed of light, everything contracts. So that's length contraction. If you lived near the speed of light, the world would seem very different than it does today. Clocks that are in uniform motion with respect to you would appear to run slow. They would lose time compared to your clock. And if you have an object that is moving past you at a high rate of speed, it would appear shorter or narrower along the direction of motion compared to when it's at rest. Let's go back to the beginning. The song 39 is a song about time travel. And the way the volunteers have traveled in time is by calling on Einstein's theory of special relativity that says moving clocks run slow. So the question is, how fast would a passenger on a spaceship have to travel such that only 1 year passes for him, but 100 years have passed on Earth? We know the time measured by a bystander back home on Earth is some boost factor times the time measured by the passenger. So the boost factor is just the ratio of those two times, and it's 100 to 1, because the people on Earth have had 100 years pass for only 1 year on that spaceship. Plug in the formula, solve it, you'll find that the speed is 99.995 the speed of light. It's almost exactly the speed of light. It's just very slightly shy of the speed of light. Now, for those of you who may have been listening at the very beginning, you might want to say, wait a minute. Wait a minute, you told us about this thing called reciprocity, which is our passenger on the train can say that the world is moving past her. And that's a perfectly valid frame of reference, and you're right. So by reciprocity, shouldn't it be that our space traveler can say, the Earth is in motion, the Earth moved away from me, and when the Earth comes back at me, shouldn't everybody on the Earth be younger than him because their clocks ran slow? The answer is no, but the explanation is a little bit subtle. I am in a state of motion is not a valid statement. Nobody has a right to say I'm in motion or I'm at rest. But my motion has changed is a valid statement. The only time that reciprocity is technically valid is when there are two inertial reference frames, one moving with respect to the other, and those inertial reference frames never, ever, ever change. But what's happened here is our space traveler starts on Earth, gets in a rocket ship, which is accelerated, that's going out of the inertial reference frame, and goes through multiple changes of reference frames. Presumably they'll slow down when they get to the distant planet, they'll turn around, they'll accelerate, they'll come back. When you undergo a massive acceleration like you're sitting on top of booster rockets, you know it, okay? The space traveler knows that his motion has changed. And so it's not a paradox because, in fact, his clocks do run slow. He is only a year older when he gets back, despite the fact 100 years have passed on Earth. Okay, reality check. Is any of this real? The answer is yes. You can measure it, but in order to understand the experiment I'm going to tell you about, we've got to go a little beyond special relativity. We've got to include gravity. So that's what we're going to do next. And then we'll come back to what's the experiment that proves it. General relativity took 10 years for Einstein to go from special relativity to general relativity. This is not simple. The basic concept behind general relativity is simple, though. General relativity is a theory of gravity, and it's much more general than Newton's theory of gravity that you probably learned in high school. Einstein doesn't say that Newton was wrong. What Einstein says is that Newton's form of gravity is a special case that only applies when gravity is very, very weak. What's it all about? Let's go back to Galileo. Galileo allegedly dropped cannonballs off the Leaning Tower of Pisa and proved that all objects accelerate at the same rate on Earth. He probably didn't do that. In fact, he probably rolled objects down inclined planes, but it's the same thing. I teach in our core natural sciences program, where in one semester for freshman non-science students, we cover all of physics, astronomy, chemistry, and earth sciences in 4 months. And one of the things we do is the great fruit drop. The second weekend of every September, we go up to the top of the economics building and we drop fruit. And we test whether or not Galileo was right. 1 banana, 2 banana, does it work? We make lots of fruit salad. Okay, so this is the great fruit drop. There's a watermelon, there's a peach. The acceleration due to gravity is 9.8 meters per second squared. Here's the ground. Take your watermelon, take your peach, hold them out, take your hands away. Neglecting air resistance, they strike the ground at exactly the same time. Okay, you knew that already. More willing suspension of disbelief. Gravity doesn't exist. Gravity does not exist. Hold out your watermelon, hold out your peach. Gravity doesn't exist. Take your hands away. If gravity doesn't exist, they're just floating there in midair. Now, accelerate the floor upwards at the same rate as gravity would pull down. The motion of the fruit relative to the ground is identical in both cases. That's general relativity in a nutshell. What Einstein says is you've got two possibilities. If all objects all different types of fruit, all cannonballs, all shoes, are observed to accelerate similarly relative to a particular reference frame, then your reference frame is either inertial and gravity is present, that's the ordinary fruit drop, or gravity is not present, but the reference frame is non-inertial, which means it's accelerating in the direction opposite to gravity. This is what's known as the equivalence principle of general relativity, that gravitation and a generic acceleration are equivalent. And in a closed environment where there's no windows to tell you the difference, there is no experiment that can distinguish between the two possibilities. Why does it matter? Well, it's actually going to matter for time and it's going to matter for distance. Effect of gravity on time. It's not obvious that gravity should affect the rate at which time runs, but it does. Ignore what's on the right for a minute. Just look at this. Imagine you have two clocks. They're identical clocks. One is going to sit on a table. The other one we're going to attach to the arm of a centrifuge. And that centrifuge is going to spin around and around and around such that the clock is moving at a constant speed in a circle. Special relativity tells you this is the clock in motion, so it should be running slow compared to that one. Okay? Technically, we pulled a cheat here, though. The clock is moving at a constant speed, but its direction of motion is changing. That's an acceleration. An acceleration is not necessarily a rate of change of speed. Technically, it's a rate of change of velocity, which is the combination of speed and direction. So because of the fact that the clock is changing direction as it's going around, even though it's at a constant speed, it's being accelerated. Now, remember back to your high school teacher who told you something about Newton's gravity. The closer you get to a planet, the more gravitational acceleration you feel. Gravity is a 1/r² force in Newton's theory. So what that says is the farther you go from a high gravity planet, the less the acceleration. And so if you sit a clock on the surface of a high gravity planet, because it's being accelerated more than a clock way up here, the clock on the surface of a high gravity planet ought to run slow compared to one that's at high altitude. So because gravitation and acceleration are equivalent, that's the foundation of general relativity, then clocks at different altitudes run at different rates. And it matters and it's measurable. First time this was done, oops, come on, there we go. First time this was done was in 1971. This was a Naval Observatory experiment with 3 atomic clocks and a couple of commercial airliners. And what they did was they took one clock and they left it at home in DC. That clock rotates with the Earth. The sun rises in the east and it sets in the west because the Earth rotates from west to east. The second clock was put on a plane and it flew from west to east around the world. That's in the direction of the Earth's motion. It's going faster than the Earth. The third clock flew backwards. It flew from east to west around the world. That's opposite to the direction of the Earth's rotation. And if you could have viewed this from space, the plane that's carrying the third clock would have appeared to just simply lift up off the Earth, and the Earth would have rotated out from underneath it. And the reason for that is the Earth is rotating much faster than a commercial airliner can actually fly. Special relativity says the second clock is moving faster than the first clock because it's flying in the direction of the Earth's rotation. So clock number 2 should run slow compared to clock number 1. Clock number 1 is moving faster than clock number 3 because it's rotating with the Earth out from underneath the plane. So clock number 3 should run fast compared to clock number 1. But our planes are at altitude, 35,000 feet. Does that matter? Yeah, you betcha, it does. The difference in acceleration due to gravity from the surface of the Earth to 35,000 feet is measurable. General relativity says just because of this difference in altitude, the two clocks that are on the plane should both run fast compared to the clock that stayed at home. The net effect predicted was that clock 2 should lose 40 billionths of a second compared to the clock that stayed at home, and clock 3 should gain 275 billionths of a second compared to the clock that stayed at home. And they got it. At the time, in the early 1970s, atomic clocks were not actually all that accurate compared to modern clocks, and that's why they had to fly around the world. You can measure this now on a flight from JFK to Heathrow. Technically, every single time you fly to Europe, you go very slightly into your future, like a couple billionths of a second. So nobody cares, but technically, that's what you've done. All right, let's pause for a moment and think about gravity as Newton viewed it and as Einstein views it. At some point, if anybody ever talked to you about Newtonian gravity, they said, well, the way to think about a planet orbiting around the sun is that gravity exerts a force, and that force tugs on the planets and makes them go around the sun. And usually the analogy that your teacher will use is you tie a string to a rock, and as you whirl the rock over your head, the string you have to pull inwards on, that's like the force of gravity. If you tie a rock to a string and you whirl it around and you whack yourself in the head, it hurts. This is a cat toy, okay? So Newton says gravity is like this. Tie a rock to a cat toy and you can spin it around in a circle. And you can try this at home with your cat's favorite toy. And you really do have to pull on the string to keep it in motion. Now, Newton's contemporaries didn't like this theory of gravity. They called it spooky action at a distance. It's at a distance because the sun is far away from the planets, and yet somehow there's an invisible string that ties the sun and the planets together. Where's the string? Einstein said, don't worry about it. Einstein said, gravity is not a classical force. A classical force is a push or a pull. Einstein said, you can't think about gravity that way. Instead, the way to think about gravity is that matter, or mass, tells space to curve. And how much mass you have determines how curved space is. And it's that curvature of space, not an invisible string, but the curvature of space that tells things how to move. If I could give you a four-dimensional analogy of the universe, I would, but I can't. I'll give you a two-dimensional analogy. Imagine you have a rubber sheet, 2 dimensions, and you stretch out that rubber sheet, and on the rubber sheet, you put weights of different masses. So there's 5 kilograms, 20 kilograms, 10 kilograms. Now, simply take a marble and roll the marble across the rubber sheet. If you're far away from any of these masses, the marble will roll straight. But if you come close to one of the masses, the marble's path is going to be deflected. It's simply going to roll around the curve in the plastic that was created by the mass. There's no string, there's no pull. It's just that the marble is moving along the curved path. And it will happen with any of these weights. And that, Einstein says, is how the planets orbit around the sun, and indeed how any orbital motion happens. This diagram here is supposed to represent the rubber sheet, where down in the center is the sun that's distorting the rubber sheet. And planets on circular orbits roll around and around and around in the same curvature here. Planets on elliptical orbits dip down and come back out again, but they're just moving on the natural curve caused by the presence of the sun that distorts, it curves space, and actually very slightly changes time as well. So, perfectly valid question. Who's right, Einstein or Newton? There are two classic tests of general relativity. One is something called the precession of the perihelion of Mercury. Perihelion is just simply the closest distance that a planet gets to the sun. And another test is something called gravitational lensing. The bottom line is that Einstein's theory of gravity gives the exact same answers as Newton's theory in the limit of extremely weak gravity. Works fine for the sun and the moon, which is what Newton formulated his theory of gravity for. But where they disagree is where gravity is particularly strong. And what that means is we have to go up very close to massive objects in the universe, like stars, or the centers of galaxies, or great big galaxy clusters. So here's Mercury, a little sketch of its orbits. Right up until the 1950s, astronomers had a very hard time predicting where Mercury would be. And the reason they had a hard time was because they were using Newton's theory of gravity. Einstein's theory of gravity says if Mercury starts off right there and it orbits around like this, the next time around it doesn't come back in exactly the same ellipse. It goes around in this ellipse, and then it goes around in this ellipse. The little spots that they've marked here are the distances of closest approach, the closest perihelions. In order to actually figure out where Mercury ought to be at any given time, you need to account for the fact that general relativity says its orbit should swing around like this. Now, it's not a big effect, but it's very definitely measurable. Every century, the total change in the location of Mercury's closest approach is 12/100ths of a degree. Small, but measurable. And you can actually even measure it for Venus and Earth, but they're even tinier because they're farther from the sun. So that's one classic test of general relativity. Here's another one. Einstein says everything has to follow the natural curvature of space-time. Not just planets, not just stars, but light as well. So here's our rubber sheet analogy. There's the sun stretching space-time down. Here's us on the Earth. Einstein says, suppose you have a star that's right there, and light from that star travels towards the Earth. It has to travel on the very curved path nearby to the sun. And what that actually means is the star is going to show up. It'll appear to be over here. The farther a star is from the sun, though, the straighter the path it takes. You should only see this if the starlight is passing right near the limb of the sun. 1918, during a solar eclipse, it was measured. So general relativity was validated over Newton's theory by the deflection of light by the sun curving space-time nearby to it. Interesting phenomenon that gravitational lensing can cause is it can give you multiple images of the same object. So imagine you have a real object out here in space. There's the sun distorting locally space. And if you have two light rays there and there that come from the distant object, those will give you two separate images of that thing right there. Before I show you the next slide, I should say, beyond using gravitational lensing as a validity test for general relativity, Einstein thought this gravitational lensing stuff was cute but useless. And the reason why he thought it was useless beyond a test of general relativity was that at the time Einstein was working, we didn't really understand what galaxies were. We understood what stars were and about how massive stars were. Einstein didn't know that if instead of the sun you use a typical galaxy, you really ought to see this. And he didn't live to see it. The first detection of a gravitational lens in the universe was 1979. That object right there and that object right there are two images of the same object that's been gravitationally lensed. The object is a quasar known as 0957 plus 561. A quasar is the very bright center of a galaxy where there is a supermassive black hole, something that's at least 100 million times as massive as the sun, that is swallowing material. You can just barely see there's kind of a lumpy fuzz right there. That lumpy fuzz is a galaxy that's causing the gravitational lensing that's giving you the two images. How do you know they're identical? You actually have to measure the light as a function of wavelength. And if you do that, it's what's called taking a spectrum, you'll discover that that thing and that thing are in fact identical. One of the most useful things about gravitational lensing is images like this. If you've ever looked through the bottom of a wine glass at, say, text in a newspaper or something, you'll see that it's all kind of wiggly and distorted. It's magnified, but it's also kind of bent around. Gravitational lenses do the same thing. Gravitational lenses make terrible eyeglasses because the images that they give you are actually highly distorted. What's going on here, this is a Hubble Space Telescope image, is that the yellow galaxies, which is what these things are living inside of a large cluster of galaxies. The cluster itself has a mass that is 10 to the 15 times the mass of the sun. If you look around and about, though, you'll see these little pieces of concentric circles. Those are very distant galaxies whose images have been gravitationally lensed by the cluster of galaxies. And it's a cute and interesting phenomenon, but it's more than that. It's images like this, a lot of which have been taken with Hubble Space Telescope, that have allowed us to measure the masses of these clusters and discover that they're mostly not made out of stars. They're mostly made out of something called dark matter, which we won't talk about today, but that's a very useful thing for gravitational lensing. All right, last thing we'll do. Think back to our song 39. The volunteers on the spaceship have aged 1 year, 100 years have passed on Earth. We figured out they had to be traveling at 99.995 the speed of light. So what would it actually take to do this? Turns out it is hard. And the reason it's going to be hard is that we're up against some limiting practicalities due to Newton's second law, that's the law of inertia, and one final oddity that comes out of relativity. So we'll do one more Gedanken experiment, and we need a train car. This time, instead of a full train car, we want a flatbed. So a flatbed railway car is going to go past us. We have two identical bricks. One's on the ground, one's on the railway platform. And the instant that the train car passes you by, you apply an identical force, that's an identical shove, to both of the bricks. What's Newton's second law? Newton's second law says that if you apply a force, call it F, to some mass, call it M, it accelerates. So when you shove on these two identical bricks with the identical force, they have to accelerate. But one of the things Einstein taught us is time is running slower on the railway car. Time is running more slowly for the brick on the railway car when you push it compared to the brick that's at rest with respect to you. And the bottom line is that the force that's felt by the brick that's on the train car lasts for less time than the brick that's on the railway platform. Say, 1/billionth of a second less compared to 2/billionths of a second. Okay? Newton says this: force is equal to mass times acceleration. If the force is applied for less time to the brick that's on the railway car, it means there has to be less effect on the moving brick's velocity. In other words, the brick that's on the train car should be accelerated less than the one that's on the railway platform. The only way that two identical forces can give you two different effects, meaning two different accelerations, is if the masses are different. So the bottom line is, Einstein says the faster an object is traveling, the greater is its mass compared to when it's at rest. How different is it? Well, the moving mass is our good old boost factor times the rest mass. The faster you go, the more mass you have. So what would it take, really, to do this? Traveling fast, which is what you need to do the time travel the way the volunteers do, takes an enormous amount of energy. The faster you go, the more your mass increases, and the more energy you need to make yourself go faster. Take a random astronaut. Let's say her mass is 75 kilograms. How much energy would it take to accelerate her up to a speed where you could do some time travel into the future? For comparison, the annual amount of energy that we in the US use is about 10 to the 20 joules. Let's say you want to accelerate your astronaut up to half the speed of light. That's a boost factor of 1.15. That's about 1% of the national energy consumption, which is a lot. Let's suppose you want to get her all the way up to where the volunteers were traveling. That was a boost factor of 100. That is like 6.7 times the annual US energy consumption. We haven't given our astronaut a spacesuit even. So add on another 80 kilograms for that, and maybe she'd like a spaceship to travel in. The shuttle is 100,000 kilograms. Okay, so it's a nice idea. In principle, it really does work. It has been measured. But it's not going to be happening anytime soon. All right, so I'm going to close out with the big takeaways, the things I want you to come away with. The first is that what we call motion is really relative. It depends upon states of motion. Intervals of time are also relative. They're not absolute. That's this thing called time dilation. Measurements of distance are also relative. They're not absolute. That's this thing called length contraction. And gravity affects both space and time. Technically, time travel into the future is possible just using special relativity, but only if you're traveling sufficiently fast, and at least for now, it's a practical impossibility. So I thank you very much for your attention, and I'm happy to take questions.